You think the speed of light is just a number. 299,792,458 meters per second. Fast. Incredibly fast. The fastest thing we know. Fine. But why is it the limit? Why can't you go faster? What actually stops you? Most people have never really thought about this. They just accept it. Einstein said so. The speed of light is the cosmic speed limit. That's just how it is. But that's not an explanation. That's just repeating a statement. When you seriously ask why nothing can go faster than light, when you dig into what is truly preventing it, you discover something so strange, so far removed from everyday experience, that it completely changes how you think about space and time. The speed of light isn't just a speed. It's not merely the fastest thing. It is the structure of the universe itself. It's woven into the fabric of space and time in such a deep way that going faster than light becomes literally meaningless. Let me show you what that means. Let's start with something simple, something everyone understands. Things fall. Drop an object and it falls downward, about 16 feet in the first second to be precise. That's what Galileo measured. Drop a ball, a rock, anything you like. After 1 second it has fallen 16 feet. Now think about the moon. The moon goes around the earth. It doesn't fall straight down. It stays up there orbiting in a circle. But is it really not falling? Think about it carefully. If the moon were just sitting still in space, gravity would pull it straight toward the earth and it would crash. But the moon is moving sideways, tangent to its orbit. Gravity pulls it inward, but because it has sideways motion, it keeps missing the earth. It is constantly falling toward the earth and constantly missing it. That is what an orbit is, continuous falling combined with enough sideways motion to keep missing. This is where Newton had his brilliant insight. The moon is about 240,000 miles from the center of the earth. We, standing on the surface, are about 4,000 miles from the center. That means the moon is about 60 times farther away than we are. Newton asked, what if gravity gets weaker with distance? What if it follows an inverse square law? That would mean if you go twice as far away, gravity becomes 4 times weaker. 3 times farther, 9 times weaker. In general, it weakens as the square of the distance. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. On Earth, objects fall about 16 feet in the first second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward the Earth by 16 feet, divided by 3,600. Do the math. 16 feet divided by 3,600 is about 1/12 of an inch per second squared. Let me say that more clearly. In 1 second, something at the moon's distance should fall toward the Earth by about 1/12 of an inch times the square of the time. Over longer times, that adds up. But calculated properly, 1/12 of an inch multiplied by 3,600 gives 16 feet, exactly what we measure on Earth. Newton calculated how far the moon should fall toward the Earth in 1 second if gravity followed an inverse square law, and it matched perfectly. The moon was falling at exactly the rate predicted by Newton's law. This was enormous. This wasn't just an abstract idea. It was a prediction that matched reality. Newton took one completely independent fact, how fast objects fall on Earth, and connected it to another completely independent fact, the moon's orbital period and its distance from the Earth. Two things that seemed unrelated were suddenly linked by a single law, the law of gravitation. There was no going back from that. Newton went further. He calculated what the shape of planetary orbits should be if gravity followed an inverse square law. He found that they should be ellipses. And that's exactly what planets do. They move in ellipses. Kepler had already measured this, but he didn't know why. Newton explained it. One law explained multiple observations. Then even more things fell into place. Take the tides. Why do tides exist? Because the moon pulls on the Earth. But wait, if the moon simply pulled the Earth toward it, shouldn't there be only one high tide per day on the side facing the moon? Yet we observe 2 high tides roughly every 12 hours. Why? Some people thought the Earth was being pulled away from the water. Others thought the water was being pulled toward the moon. Both ideas had part of the truth, but neither was complete. Newton realized what was really happening. The moon pulls on the Earth and the oceans with nearly the same force, but not exactly. The water on the side of the Earth closest to the moon is closer than the Earth's center, so it is pulled slightly more strongly. The water on the far side is farther away than the Earth's center, so it is pulled less strongly. As a result, you get two bulges, one where the water is pulled more toward the moon and one where the water is left behind because the Earth itself is pulled more strongly than that distant water. That gives 2 tides per day. Another way to see it is that the Earth and Moon both orbit their common center of mass, which lies somewhere inside the Earth. The centrifugal effects are slightly different for different parts of the Earth and its oceans. Either way you describe it, the result is the same, 2 tides per day. Many other things became clear as well. Why is the Earth round? Because gravity pulls everything inward toward the center. Why isn't it perfectly round? Because it's spinning, and the rotation causes the equator to bulge slightly outward. The same reasoning explains why the sun, the moon, and other large bodies are round. As science advanced and measurements became more precise, Newton's law was tested more and more rigorously. One of the first really careful tests involved the moons of Jupiter. By observing their motions over long periods of time, astronomers could check whether everything behaved exactly as Newton's laws predicted. At first, it seemed they didn't. The moons of Jupiter appeared to be sometimes about 8 minutes ahead of schedule and sometimes about 8 minutes behind schedule, where schedule meant the times predicted by Newton's calculations. 8 minutes is a huge discrepancy. Something was wrong. Then an odd pattern was noticed. The moons appeared ahead of schedule when Jupiter was closer to Earth and behind schedule when Jupiter was farther away. That was strange. An astronomer named Rømer, who had great confidence in the law of gravitation, came to a remarkable conclusion. Light takes time to travel from Jupiter's moons to Earth. What we see is not how the moons are now, but how they were some time ago. When Jupiter is closer, the light has less distance to travel, so we see the moons sooner. When Jupiter is farther away, the light takes longer to reach us, so we see the moons later. By correcting for this effect, by accounting for the extra or reduced travel time of light, Rømer was able to determine the speed of light. This was the first demonstration that light does not propagate instantaneously. Think about what just happened. The speed of light was discovered not by directly measuring light itself, but by trusting the law of gravitation. When observations didn't match predictions, instead of throwing out Newton's law, Rømer asked whether something else might be going on. He realized light had a finite speed, and he's right. This illustrates something important. When a law is correct, it can be used to discover other laws. Confidence in one correct theory can reveal entirely new phenomena. If we hadn't known the law of gravitation, it would have taken much longer to discover the speed of light, because we wouldn't have known what to expect from Jupiter's moons. This process turned into an avalanche of discovery. Each new discovery became a tool for making even more discoveries. That avalanche began hundreds of years ago and is still ongoing today. But here's where things get truly strange. Once you know the speed of light and measure it carefully, you start noticing something deeply unsettling. Light always travels at the same speed. Always. No matter who measures it. No matter how fast the observer is moving. Let's make this concrete. You're standing still and you shine a flashlight. You measure the speed of the light. You get 299,792,458 meters per second. Fine. Now you get on a train moving very fast, say half the speed of light. You shine the flashlight forward in the direction the train is moving. Common sense says the light should be moving at the speed of light plus the speed of the train. Just like throwing a ball forward from a moving train makes the ball move faster relative to the ground. But that's not what happens. You measure the light again. It's still traveling at 299,792,458 meters per second. You think you must have made a mistake. You make the train go even faster, 90% the speed of light. You shine the flashlight forward, you measure it again, same result. You push it to 99.9999% the speed of light. You shine the flashlight, still the same speed. The rate of light does not add. It does not combine with your motion. It is always the same, no matter how fast you are moving. This should completely break your intuition. This is not how motion works in everyday life. In everyday experience, speeds add. If a train moves at 50 miles per hour and you walk forward at 3 miles per hour, you move at 53 miles per hour relative to the ground. Light doesn't behave like that. Einstein realized what this meant, and the conclusion was shocking. Space and time themselves are not fixed. They are flexible. They adjust to preserve the speed of light. When you move faster, time slows down for you. Your clock really does tick more slowly. Distances in the direction of motion contract. Space itself becomes compressed. These effects are not illusions. They are not measurement errors. Time actually slows down. Space actually shrinks. And the amount by which they change is exactly what's required to make the speed of light come out the same for everyone. Let me say that again. The universe bends time and stretches or compresses space so that light always travels at the same speed for every observer. The speed of light is not just a speed. It is a structural constant of the universe. Space and time are arranged so that this speed is the same for everyone. Now it gets even stranger. If you try to accelerate any object with mass toward the speed of light, something remarkable happens. The closer you get, the harder it becomes to go any faster. This isn't because your engine runs out of power or fuel. It's because the object itself resists acceleration more and more. This is called relativistic mass increase, or more accurately, an increase in inertia. As your speed increases, your resistance to acceleration increases. As you approach the speed of light, this resistance approaches infinity. To actually reach the speed of light, you would need infinite energy. That's impossible. So nothing with mass can ever reach the speed of light. Not because of an arbitrary rule, not because of technological limitations, but because the structure of space-time itself forbids it. Light can travel at that speed because photons have no mass, zero. Massless particles travel at the speed of light. In fact, they must. They have no option to move slower. Anything with mass can get very close, 99.9999% of the speed of light, but never quite reach it. The universe simply will not allow it. And now you might ask, but why? Why is the universe set up this way? Why is there a speed limit at all? And here's the answer that's going to frustrate you. There isn't a deeper why. The speed of light is not a speed limit imposed on the universe. It's a consequence of how the universe is structured. Space and time are not separate things. They are woven together into space-time, and space-time has a geometry, a structure. That structure has a built-in conversion factor between space and time, and that conversion factor is the speed of light. It's not that light itself is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light happens to travel at that rate because light has no mass, but the rate itself is a property of space-time, not of light. Even if light didn't exist, the speed limit would still be there. It's a feature of the universe itself. Here's another way to think about it. In everyday life, you think of space and time as separate. You move through space, time passes. They seem independent, but they're not. You are always moving through space-time at a constant rate. Always, that motion is divided between space and time. If you're sitting still, all of your motion is through time. You're moving into the future at the maximum rate, 1 second per second. But if you start moving through space, some of that motion has to be diverted away from time. Now you're moving through both space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time, and there's a limit. If you could move through space at the speed of light, you would have no motion left for time at all. Time would stop for you. This is why light doesn't experience time. From a photon's perspective, it's emitted and absorbed in the same instant. No time passes. The universe is frozen. You can't go faster than light because you can't have less than zero motion through time. That's the limit. That's the wall. And here's the beautiful part. This isn't just theory. It's been tested again and again. Particles and accelerators are pushed to 99.999% of the speed of light. And the closer they get, the harder it becomes to accelerate them further. Exactly as predicted. GPS satellites have to account for time dilation. They're moving fast, and they're in a weaker gravitational field, so time passes differently for them than it does for us on Earth. If we didn't correct for this, GPS would drift by miles in a single day. Muons created high in the atmosphere by cosmic rays should decay long before reaching the ground. Their lifetime is too short, but they're moving close to the speed of light, so time slows down for them. From their perspective, they live long enough to reach the surface. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than should, exactly as relativity predicts. This isn't speculatio. And it's measured. The speed of light being a limit is as well tested as anything in physics. So let's put it all together. Why is the speed of light the limit? Because space-time is structured in a way that has a maximum rate at which cause and effect can occur. That rate is the speed of light, not because light is special, but because space-time itself has a built-in relationship between space and time. You can't go faster, because going faster would require moving backward in time. And that doesn't make sense. You can't have negative time. You can't undo cause and effect. The speed of light, the speed that this now propagates through the universe. It's the speed at which information travels. It's the speed at which forces act. It's the maximum rate of change. And this whole story, this avalanche of discoveries, started with Newton figuring out gravity by watching the moon. Then Rømer figuring out the speed of light by watching Jupiter's moons. Then Einstein realizing the speed of light is constant and building relativity on that insight. Then thousands of experiments confirming it again and again, each discovery built on the last. Each new insight opened the door to more insights. That's how science works. That's the avalanche that's been going on for about 400 years. And we're still avalanching forward at high speed. The speed of light isn't just a number, it's the key. It's what unlocks how space and time really work. It shows us that the universe is stranger and more beautiful than we ever imagined. And the fact that we can understand it, measure it, test it, and use it to make predictions, that's the beauty of physics. Not comfort, not simplicity, truth.